networks, including as a founder and vice president. Professor Ramakrishnan is an ACM fellow, IEEE fellow, and an AT&T fellow, recognized for his fundamental contributions in communication networks, congestion control, traffic management, VPN services, and a lasting impact on AT&T and the industry. His work on DEC bit congestion avoidance protocol received the ACM SIGCOMM Test of the Time Paper Award in 2006. He received the ACM SIGCOMM Lifetime Achievement Award in 2024. He has published over 300 papers and over 180 patents issued in his name. He received his MTech from the Indian Institute of Science in 1978, MS and PhD in computer science from the University of Maryland, College Park, USA. Over to you, Professor.
I should be okay now. Thanks. Thank you. I wanted to come last year. Actually, I was supposed to come in December of 23. Finally got to make it. We've been working on this serverless computing for a while, and I know the hot area right now is to look at what you can do in machine learning, but I think there are some lessons here to take away, even when you're looking at how to use computing for ML applications that run in the cloud. And so I'm hoping that this will be relevant in that context. So if you look at how people are building applications, one of the things that we tend to do is build applications as a sequence of microservices. And the reason that people tend to do that is development flexibility, so that each component is easily designed and you can pull them together, and you basically couple them together and they can run wherever they need to. And in the process, each one is independently scalable. So if you have something that is a bottleneck for some, even not necessarily consistently, but for a short period of time, then you can scale that particular component independently rather than scaling the entire environment. So this approach has become really quite popular for building software-based applications. And even in networking, when we think about things like network function virtualization and so on, this is how we end up building systems. Now, one of the things that we see as a natural follow-on is to be able to now think about how developers can actually have each one of these components deployed in the cloud. And we tend to do that using this approach called serverless computing, and that's really one of the faster growing cloud offerings. If you look at where people are investing, a lot of the cloud investment is going into serverless computing, mainly because from a consumer standpoint, it helps tremendously in terms of the user having to focus on how they deploy their applications in the cloud. They basically build the function code and they leave the rest to the cloud provider to manage. It makes primarily on their application rather than having to worry about how to configure that application, how to do it, and so on. And the characteristic of these serverless applications is that it's entirely event-driven. So you make a request, that application runs, resources are provisioned for running that request, and then once it's done, it's gone. You don't maintain state, and it's really short running. Volume, I think. Okay, so the benefit of the serverless computing is that you really don't have the need for the cloud to have resources provisioned and running constantly. Okay, you just have to run it when the request is there. Think about IoT like services. So you have a request maybe infrequently. You don't want to have resources committed for all the period when you just one request coming once an hour that you need to process, right? And from a user's perspective, they're only paying the cost for processing that request, not for running the resources all the time. Allows then for the resources that are there to be multiplexed across many other applications. So it improves scalability and availability as well. The one thing that we find with serverless is that because it's stateless, it's event-driven. You have a failure, you now just invoke the request somewhere else, you instantiate that function again, and then you are off and running. So the burden is in the cloud provider. She has to deal with provisioning, managing, all of that. So if you look at overall what the cloud is managing, they're managing all the hardware, they're managing the virtualization, the OS, provisioning, all of that, and the user only cares about building the application and whatever user data that they need to have. So this event-driven execution is very desirable from the point of view of, okay, and it's sort of true pay-as-you-go billing from the user's perspective. This is what we call a function as a service rather than software as a service. It's going one step beyond. So if you think about cloud computing, what we're trying to do with cloud computing is getting multiplexing of the system and software across multiple demands. Now, when you think about serverless, it's actually going to the extreme in terms of being able to multiplex as much as possible, right? Rather than between tenants, it's actually saying I can multiplex at the level of individual requests, right? So what you end up doing is now offering the service as, look, I can offer a function as a service. So if you are a vendor of a product, you can offer that software as a function that you export, so people can just make requests to that function. And that function runs on the cloud and goes away when you don't have any requests. Okay, so if you look at the way a cloud service provider provisions this in the cloud, you have two broad pieces. One is the data plane where the requests are handled, and the control plane where you're managing the resources. You have requests coming in from the user. Let's say that you're doing a purchase request like we saw in the previous slide. This is a typical, boutique service that you might have online, right? So what we end up doing is making those requests. Those requests are coming into some kind of an ingress gateway that says, okay, I will terminate the request, verify that it is a valid request, and then check for its authorization. At that point, I know that this service is being offered. I'm going to pass that on to the appropriate function or trigger that function to be executed. So that request then has to be delivered to the right function container. That function container might be running or it might be created. So you end up having to then have it go through some kind of a broker. That broker says, well, I now am going to route this request to a particular function. And that function has a proxy, we call it a sidecar, and that has become a very popular way of how people manage services. They have basically a proxy that says, well, I'll take the request, I'll front end it, and deliver the payload of that request to the function container. And once that request is processed and I have to go to the next function, I pass it back to the message broker, and then the message broker forwards that function, the request, to the next function, and so on. The sidecar, that is the proxy, is doing a bunch of things to help the control plane. It collects all the metrics about the request rate and so on, so that we know how much load is there on that function container, so that I can then provision accordingly. So I take all of that metrics and hand it off to the control plane. The main control plane is doing is what the cloud service provider does, which is to scale the services that are needed as the demand requires. And then based on the large scale data center that you might have, you then place those function containers in the appropriate servers. Okay, so what people have done is to say, well, this is a very convenient paradigm. Let me stitch together existing approaches for how these functions can be connected together. So if you look at the process, I'm going to go through a little bit step by step so it's easy to understand how the process works. You basically have a request coming in, and virtualization means you go through a virtual Ethernet interface and then go through the kernel protocol stack to then deliver the request to a container where it's doing the ingress function of authorization and authentication. So you end up having to go through essentially dealing with a HTTP request that comes from the network to this, what might be basically a NGINX proxy, if you will. So that's the ingress gateway. And when you look at the work that has to be done, you end up getting an interrupt. Again here, processing, and then you say, well, I have to do a context switch to get that request up to the container. And in the process, I'm going to have to move data from the kernel to user space, and I'm going to do deserialization so that now the payload is available for this guy to do all the authentication and authorization. Okay, once he's done all that, we've gone through a bunch of overhead for doing that work. Once we've done that, we then say, well, I know that I need to get it to the message broker. And usually what ends up happening is that we go through this kernel protocol stack. We don't go over the network, but we're going to another container. So one container to another. Container networking is what we end up using. So we go through the kernel protocol stack, somewhat less complex than what it was before, but then we eventually get it to the message broker. We go through the whole process of doing networking, going out, and then back up again. So in the process, we can look at the amount of overhead that happens. Once that work is done at the message broker, then we say, well, I've got to get it to that function container. To get it to that function container, we get to the sidecar, that's the proxy here, for that function. And from that sidecar, we would get it to the actual function container. So if you look at all of that processing, you've got all of those overheads happen all over again. Whole bunch of copies, context switches, protocol processing, and so on, just to get from one container to another inside the same node. And once that function is completed, let's say that you have a simple application that has two functions. Then you have the request having to go to the second function, but these are stateless. They have no idea how you're going to route from this function container this one, because you have no idea where this was placed. Right? So you end up now having to get it to the message broker, suffer through all those overheads, and then afterwards that message broker says, well, I now know to send it to the second function. And then go through the same process, eventually then get the response back through this ingress gateway out to the client. So very simple, and this is very easy to put together, but lots and lots and lots of overhead. So the sidecar here is acting as a proxy to the function that is running in that container. So it's basically saying I'm going to receive the request. It looks like a HTTP request. Okay, so I'm going to take apart and find the payload, verify that it is the way it has to be presented to the function container, deserialize it so that you have the structure the way that the call for this function works, because you basically just written a function with parameters, right? So you have to present it to this function in the way it can handle it. Exactly. And that's what all of these proxies tend to do, okay? But there are 2, 3 other critical things that they have to do as well. They have to monitor the health of this guy. If he fails, this sidecar works with the control plane to make sure that you restart another one. If this is overloaded, the statistics that you provide is helpful for the control plane to decide how I scale this up, right? So the sidecar plays a critical role. You need the work that it does. And in the process though, the problem is that this has to run all the time, even when this is not alive. So it sort of obviates or nullifies one of the significant goals that we have with the serverless, which is that we don't want any resources to be used when the request is not alive, right? And that ends up being, you pull the rug under that. So we look at how to overcome that as well. Nothing is inevitable if you go back and look carefully. It's part of the control plane, yes. And so my main complaint is this overhead, okay? And I said, yeah, it's inevitable. Let me try to make this as cheap as possible. After a little while, I said, let me try to get rid of it. And what we've tried to do is actually get rid of it. So the 2 things that we are concerned about is one, which is this inevitable thing, which is that we have components that are constantly running, they're stateful, and they're running in user space. So the sidecar, there's a message broker. You say the message broker is also inevitable, right? And you must have heard of something called Kafka. It's a god-awful heavyweight thing. And that uses up so much resources. And the ingress gateway is another one. You have to have a way of dealing with the request coming in. You have to have a way of dealing with, verifying that it is a legitimate request and so on. These are all things that you have to do. You have to do it more sensibly. And it really results in a lot of inefficiency. And this kernel-based networking, to make it very easy to communicate, is tremendous in terms of resource consumption. So what we said was, especially this aspect about inevitability of the sidecar. You've heard of TCP dump from long ago. That was based on this notion of Berkeley Packet Filter, right? So what we have in the operating system kernel is these hook points where you can add a piece of code, right? And that piece of code is basically running in the kernel context, but working on behalf of the application. So we said, can we use that instead of the sidecar? So it becomes not inevitable, right? Very simple idea, but very useful. So what we said was, can we use this eBPF? And people are working on it quite a bit now. It becomes an ideal capability for this event-driven execution, because BPF is triggered when you hit that hook point in the kernel. When you have a request coming in, when you have a request going out, whatever is the thing that causes that particular kernel call, then only you're executing. You're not running it at all at other times. So this eBPF, we end up using it to replace that sidecar. So we've gotten rid of something that is constantly running. We A message broker, what is it doing? It's saying, I'm getting a request. I have to now forward it to the right receiver. I can also replace that with a piece of eBPF code. So if I look at what eBPF is doing, right, it's basically saying, I've got a user code, okay? Think about it as being written in C. That C code needs to now be attached to that hook in the kernel. Like if you have a socket, you're attaching to that socket hook point the code. And if this is just metrics collection about receiving or sending packets, you can have this eBPF code inserted at that hook point. What we tend to do is to have a verifier that says, well, is this code safe so that it doesn't crash the kernel? So there are a bunch of restrictions that they have with BPF. We've actually looked at how we can ease some of it, but nonetheless, it's important to make sure that the kernel is safe. And after that, you can then say, well, once it's verified, I can insert it at that hook point, right? So the stuff that I have to have as sidecar can now run purely event-driven, okay? The other piece that people have done over the recent past is to have this notion of a eBPF map. Okay, that's basically a small amount of data structure. It's limited. We would like it to be larger, but it's a limited data structure that can keep state. It's keeping state in the kernel on behalf of the user's context. Okay, and that can now be used to keep state. And that we use that for keeping routing state so that the message broker work can be done using eBPF code with that map. Okay, so think about what happens when you have a packet that has to be sent out. Okay, you're going through the socket to send it out to the next function, right? And so you're invoking that eBPF hook point, it's running that code, it's updating the statistics over here in the eBPF map, and that can then go to the control plane. Okay, so it becomes relatively lightweight, tremendously actually lightweight if you look at the amount of resources that we consume, and it is now truly event-driven. How does it go to function 2? That is what we were going through the message broker to do that intermediary function of routing, right? Now, I don't need to do that. I can keep that routing over here, right? And I can then do direct function routing. I was going to come to that in the next step. Okay. Yes, sir. So if there's a failure, right, what you need is for the control plane to actually manage that failure, right? So the control plane is waiting for the sidecar to provide notifications. What it does almost everywhere when we deal with failure resilience is by basically doing keep alives, right? And I keep doing a keep alive just like we do on WhatsApp messages about saying good morning, right? When you don't, you know the other person hasn't woken up. So that's basically what the control plane is doing here, right? And so the burden has always been on the control plane. It's not been on the sidecar. The sidecar is providing a notification, right? And you can do the same thing over here. No, eBPF sends that heartbeat notification, right? Right? So the lack of the heartbeat notification is what you need on the control plane to decide what to do. So I'm using that map for more than routing. I'm using it for statistics collection as well. So there is a issue with the map because the kernel says, look, I don't want to have a huge data structure that now occupies a lot of kernel space, right? So what we try to do is to see how to manage that carefully. But again, that is an issue. So there are a whole bunch of these hook points in the kernel, whether it's in the socket, whether people are actually using eBPF now to customize congestion control protocols for different applications. And if you look at how people are using Quick, different components of Quick are now being customized based on application using eBPF. You can do it at the virtual Ethernet interface. You can do it at the device driver. The main thing is that you can load these pieces of code dynamically, right? And you don't have to change the kernel. You don't have to compile the kernel all over again. It's transparent to the user function as well, right? And the stateful processing we can use using this eBPF map. And it helps in retaining routes. It helps in retaining metrics. So, okay, so what I'm looking at here is there are hook points over here that can now be used to invoke code that changes the way you actually have TCP work, right? And if you look at what we do with Quick, it's a user space protocol. But there are a bunch of things that you can do now to customize based on different users and different applications by having that hook point over here at this interface. So you can actually make changes to the way that the protocol itself operates. Interoperability, safety, bugs, all of that are issues without a doubt. And in our context, for the serverless thing, it's been very powerful because the functionality that you need is very simple, clear, well-defined, right? But the thing is, it doesn't protect you from yourself. So what we end up doing is bypass the kernel. Well, this is one thing with eBPF, okay? Now, with kernel-based protocol processing over here, we go through all this switching and copying, right? Now, what we've done for ages now, for well over 10 years, is looked at how among virtualized components, we can use shared memory, okay? Because you can now have very simple information exchange between VMs, containers, whatever they may be, through the shared memory. So what we end up having is a way of just simply doing pass by reference by having a descriptor to pass a reference to this data structure that is in the shared memory pool, right? So when we get data, let me actually get to another slide to describe a little bit more in detail about how we use shared memory. So the first thing that we did was to use this eBPF sidecar to get rid of these constantly running components. And we ended up saying, we'll use the shared memory to reduce all of this data movement, overhead, and context switching. And for going between functions, we said rather than going through the broker as the intermediary, we simplify it and just directly go from one function to another. Okay? Let me actually get to the... So whatever your function graph is, right, that has to be represented in your routing. What we do is represent that routing in this message broker by the data structure that represents going from function 1 to multiple instances of function 2 by having the whatever load balancing you want to do. So every instance of function 2 that you create, you're going to have that message broker have that routing inserted for that instance of function 2, right? And if you have a function graph that says, well, based on this state, I'm going to go from function 1 to function 2. Based on the state, I'm going to go from function 1 to function 3. So that routing is stateful also, that you have to have the message broker have that. Map and code, right? Right? So the code is stateless. The map is where the state for the routing and taking the current state into account. So we end up saying, look, I can actually now have all of the traffic filtering, all of the routing work and metrics collection all be done in this at the socket hook. So for protocol processing, what we end up doing is we consolidate all the initial protocol processing that comes in from the external world into ingress gateway, and then we move the payload into shared memory, okay? And it stays there in its resting place. And all of the sharing of information from that ingress gateway to function 1 and then on to function 2 is all done by pass by reference. All we are doing is passing a descriptor from one function to another. So ease of development means I take things that are built already and stitch them together, right? We know how to make HTTP work. We know how to make REST API work. We know how to take two things that talk to each other and make them stay apart. And you use REST API and HTTP protocol for communicating between them. So let's just continue to use that. It doesn't matter whether they're running on the same node or anywhere else. So we can build services and offer them easily. But the problem is that we have a lot of resource wastage, right? But if you have a nuclear power plant that is feeding a data center and you have enough money from the stockholders to build a data center that is running at 5% utilization, it doesn't matter. You can continue to be profligate about how you use your resources, right? So that's why we see that this is something that you can, if you start doing things sensibly, you can tremendously improve how you use resources, right? And so all you're doing then is moving the payload once into shared memory, stay there, and then send it out eventually. So this pass by references also, we use these eBPF hook points to be able to deliver the references from one function to another. How
if you're applying function to do something, one thing like, let's say function is a function f, like schedule input as x, apply f1, I get f, and I'm gonna write back, f of x, not x itself, right? And now f was actually f1, like f2 and f1 of x. So there will be a lot of.
So what happens is there is read and write into memory, right? But it's not the network I/O that we typically think of, which is to move the data from one memory location to another, and by attaching headers, removing headers, serializing, deserializing, all of that work, right? We are basically updating in place. Now, what we do for delivering these references is we have a producer, and that producer is doing a write, and the consumers now have a descriptor that has either read or write capability, right? So we allow for a single writer, multiple readers, but only the guy who has write ownership can update, right? So when I pass this function to the second guy, I pass the ability to write over here, but nobody else can read. So, and this has another very important piece, which is that implicitly you have the lock on who is able to read or write, right? So now we don't have to have locks to access that memory. Okay. So when I look at overall with all the things that we did, within the chain, what ended up consuming a lot of data copies and context switches and protocol processing, we got rid of most of them. Okay? So yes, we've got an ingress that gets data from outside. We've got to do that processing inevitably, and there is some inevitability there. But the rest of it, we can eliminate a lot of the overhead. So those are either hardware or software interrupts, right? And actually, originally what we started off doing was we used DPDK, and DPDK does polling. And we built a system focused around DPDK and polling, but we found that that ended up consuming lots of resources. So we've actually resorted to using software interrupts and this eBPF hook points to reduce that overhead as well. And that's why we still have some amount of software interrupts and context switches that are still involved. But otherwise, most of the other overhead is completely gone. And so if you look at, we've done a bunch of things. There was a paper in SIGCOMM, and actually after that, we take the same framework and built a lightweight federated learning platform as well. And now what we're doing is looking at using the same framework, extended a little bit to look at this LLM MOE model where each expert can now be a serverless component. But we look at this particular application because it's one that many people have looked at for how serverless performs. It's basically a typical application of consumer to business interface. And we said, let's look at how it performs. If you didn't have serverless at all, you're just doing simple microservices using RPC, the performance that we got with the system that we built was about that. Okay? Typical open source serverless framework that is Knative, and it's quite representative of what we see with the production serverless platforms as well, like Lambda and so on. It's just a little bit worse than pure RPC, but it gives you some of the other benefits of just not having to have constantly running components. On the other hand, when we look at our approach, it gives us about 5 times better performance. And if you look at the tail latency, one of the things with serverless is that you say, well, I'm going to make a request. If that request is coming to a function which doesn't have a function container running, then you have to instantiate that function. That's going to take some time. They call it cold start, and that takes a big hit in terms of latency, which if you're constantly running, you don't have that hit at all. So you get these red gRPC performance for response time tail 95th percentile, which is very good. And what we see is because of our lightweight processing, we get even better than that. These are all the cold start triggers that you end up suffering, right? It takes you 1.5 seconds to start a function container. Now, with with our approach, we consume about 3 CPU cores for running this application at this kind of performance. So about 5 times or 6 times better than a typical serverless environment. But we are using only about 10% of the CPU. Huh. So the thing that we are doing, what are we going to have to cold start? It's the function container if it's not running. With SPRIGHT, what we see is that when it's not running, it's not consuming any CPU resources at all, right? There's no sidecar that is constantly running. There's no message broker that's constantly running. So it's completely event driven. So you don't have to kill it with as tight time window for inactivity. So we can completely sidestep this whole problem of cold start. So we don't have to kill it, which means we don't have to start it. It's running. It's there. As long as you have memory, that's the one penalty we pay. As long as you have memory for keeping that function alive, you're not consuming any CPU resources. And so you don't have to start. It's always running, right? Always running in the sense of it's active. So as long as you have enough memory and you have the data structures in the operating system to be able to run that many processes, then you don't have an issue at all. I have a whole other talk, but I'm going very slowly, so I'm going to just quickly go through 1 or 2 pieces of it. But the main idea is that we took this idea of eBPF to be able to reduce this long-running components and make it all truly event-driven. So in the process, we said serverless actually can truly be like what it was meant to be, which was event-driven serverless capability. And the shared memory processing has helped us to streamline the data plane considerably. The one price that we still pay is the one that you asked. Hey, if I have like the standard serverless framework, I have to create the container. That's the startup. And then I've got all this other work. In SPRIGHT, if I don't defy when I kill the container and I kill it very quickly, then I still have to suffer this overhead of creating it. There's no magic there. All we do is we don't kill it quite as often because we don't pay the penalty of it being alive as much. So we said, how can we get rid of this? This is not going away even in our environment, and we'd like to find a way of doing that. So there is the overhead of this runtime and having to do this creation of runtimes versus isolation. So one of the things that people have been looking at for ages is to say, well, I favor using VMs because of the strong isolation, whereas containers don't have as good isolation, but they're a little bit faster in startup. So there's one other aspect that we found can be helpful here for that fast start, which is to use unikernels. Okay, because now you've got basically this function. There's really no reason to run it in a full-fledged container. You can run it in a single address space. Okay, so we've basically said I can use unikernel compared to a Docker container. It gives me 4 or 5 times faster startup. So the same ideas that we had with SPRIGHT that is running in a containerized environment, we can now run in a unikernel environment. The function is running in a unikernel. So it's basically a VM, it's a single address space kernel. Okay, so you've got a library OS and you've got all the things that you need in that single address space. So your creation is very rapid because you're not running a full-fledged environment that is like a container. So we said, can we take all our ideas and now build it in a unikernel environment. The issue with that is that if you look at what we did with shared memory, that shared memory idea is wonderful in terms of being able to get efficiency, but it can end up being a conduit for data leakage. And especially if you have buggy behavior. So we said, how can we make sure that we can address these concerns about sharing? Between kernels, between say functions, if they're not trusting each other, you need to make sure that that shared memory is managed carefully. And within a unikernel, if you've got modules that are running in that library OS that the system is trusting to be trustworthy, then if it's running in that single address space, it can be buggy as well, or it can be malicious. And so what we want to do is to make sure that what is user code that is not trusted is separate from what is a trusted computing base that is running in the unikernel. So what we ended up doing is to say that we will make a unikernel environment that is secure and still have all of the capabilities that we talked about of having event-driven functionality and still being able to take advantage of shared memory. So eBPF runs in the kernel, right? Now what we have is an environment in a unikernel where everything is in the single address space. There is no separate kernel. It's all within that user, and all of the library functions that are needed are all within that single address space. Okay, so what we said was, instead of these sidecars being eBPF, now we'll create them as library functions, but what we need to do is to make sure that those are protected. Okay, and same way, accessing that shared memory, if we've got functions that trust each other, they can access shared memory directly, but if they don't, then you need to make sure that they're protected. So there's a piece of work that Intel has introduced on their processors called MPK, memory protection keys. And so we use those memory protection keys with what we call a call gate, which is basically a shim that allows for memory protection keys to be modified only through that shim to make sure that we then isolate and provide the security that is needed in this unikernel environment. I want to skip through a lot of the detail and just get to saying, look, if I use this unikernel environment, I get a tremendous amount of performance improvement. The overall framework is to say that in a worker node, I say that each one of these secure unikernels basically have two pieces. One is user code, and then I've got basically a trusted computing base, which has the scheduler, the booting for the unikernel, the page tables, the sidecar, the network IO library, all of that is protected using this MPK. And MPK works basically by saying, I'll have basically a register. Okay, it's a 32-bit register. It's got basically 2 bits for each of 16 different keys. Okay, these memory protection keys are then used to decide how each page in memory can be managed. Okay, and that you basically have these to say, well, is this page read, write, or no access? And so we manage the access to the page tables, and using this MPK, we can then protect the sidecar, we can protect the shared memory. And rather than going through a lot of the detail, let me get to So that same application that I showed you, and we compare it with our own work, with that SPRIGHT work. And what we see is that with this very lightweight unikernels, we're able to get an order of magnitude better performance. It's because the work that you do is really much more focused on exactly the work that you need to do for each function. Okay, so if you look at even compared to our SPRIGHT, we're seeing that the RPS going within the same node, and even when we go across nodes, it's a huge improvement. Request per second. And if you look at the CPU efficiency, we are comparable to SPRIGHT. I didn't want to go, the getting through that MPK will take me another half an hour. I went much slower than I expected to. But the idea is that using this event-driven capability that you have with these hook points, with eBPF, with a container-based environment where you've got a kernel, it is a tremendous benefit in terms of resource management. And the same idea we're able to now use with this idea of having a library-based sidecar. So we create a library that gets compiled along with the rest of the function in that unikernel environment, and that's able to give us that much faster startup. So we can now not worry so much about that cold start latency as well. Okay, and this MPK-based idea is really great for being able to have very fine-grained memory access. We can deal with any potential memory space sharing vulnerabilities, and also, especially for these library-based sidecars, we can protect that library-based sidecar so that we can protect the integrity of the system, and gets quite a bit of improvement in performance. Okay, I'm done. Thank you.
Thank you very much, Professor, for an interactive talk. I request the audience to pose questions if any.
There is an equivalent with AMD processors as well, but we focused on the MPK that comes with Intel processors. I don't know about ARM, but with Intel, we're able to use it. And the thing that I see is that the overhead is so lightweight. So I look at using our library-based sidecar, including using MPK. Okay, and we said, well, forget about sidecars entirely, and look at what kind of performance we get with just running it free without having any of that work. And in contrast, if you say, well, let me use NGINX, which is a somewhat heavyweight component, but one that is easy to put together, performance is terrible. But with our library-based sidecar providing all the functionality that we need for a sidecar, the penalty in terms of performance is negligible. So the MPK overhead is also quite small. I wanted to show this. This graph where it's hard to, but the overhead with MPK is really quite negligible. In the past, Intel had this thing of enclaves and SGX. That's heavyweight. And compared to that, this capability of using MPX and one of the MPK, and one of the things that we needed to do was be careful about how we use MPK. For some components, we want to directly change the register. For other components, we want to change the page table entry. If you change the page table entry, then you have a TLB flush. So that becomes a penalty. So you have to be very careful about how you use it, but by using it very judiciously, the price we pay for using MPK is very, very small. Yes. And they've done it, we've leveraged it. It's relatively recent, 2019, 2020, around that time. Processes from then onwards have it. On the table. Yeah. So I wanted to look at what happens in terms of throughput if I didn't have a sidecar at all, like got rid of it completely, which is basically saying what's the load that the sidecar introduces versus you get rid of it entirely. And we said by having this library-based sidecar, which is basically driven functionality that is in that library rather than in eBPF, you're paying very little penalty. In terms of throughput, in terms of delay, and in terms of CPU cycles. Very little consumption of cycles.
Any more questions?
Okay.
I hope there are no more questions, Professor. So if you guys want to talk with Professor, or if you have some more questions to talk to discuss with, please feel free to do so by having a cup of tea at the EC Coffee Hut. Thank you all for attending and have a great evening. Thank you.
Thank you.